Okay, guys, you don't mind if we put our recording on YouTube?
Not at all. That'd be great.
Okay, great. We'll still wait a couple of minutes before you start, okay?
Sounds good.
Gus, could you please send your notes to the chat before you start?
Of course, yeah, will do.
Thank you.
Okay, so just have you put your notes
not yet. Maybe I can send them right now, actually.
Yeah, please.
Good? Yeah, will do. Let me figure out. One moment. And where should I send them?
Just put it on the chart.
On the
chart. There is a chart.
On the chart?
Yeah.
Let me see if I can. First, let me put them to my laptop, and then. So the chart is on the seminar website, or?
No, the chart of our meeting.
The chat. Yeah, yes, of course.
Yes, just the Zoom chat.
Good. Let me do that. Where are we? Chat.
There is a chart button at the.
Yeah, I think I've got it. Let's see. Okay, there we go. Should be loading now.
Okay.
Good. Sorry about that.
Okay.
Thank you.
Okay, great. So let me see if we are stabilizing more or less. Okay. It's my pleasure to introduce Gus Schrader from Columbia University. Okay.
Okay, well, yeah.
You are a host now.
Great, sounds good. So yeah, first of all, thanks very much to everybody for having me. I'd also like to say that it's, as you probably already figured out, it's my first time giving a seminar in this post-apocalyptic format. So in the event of any kind of technical problems or my going too slow or too quickly, please, jump in and let me know, and I'll try and remedy things. Okay, so so the topic of my talk is going to be kind of an alternative functional representation of the double affine Hecke algebra of type A. So I think it'd be good to begin by giving a quick reminder of what kind of objects these double affine Hecke algebras actually are. Okay, so so what's the basic idea? Again, in the talk, we'll be confining ourselves to the case of type AN, and really more specifically, the double affine Hecke algebra associated to GLN. And the basic kind of algebraic topological setting is the following. So we start out by thinking about the configuration space of n points on a two-dimensional torus. Okay, so the fundamental group of this this space, conf T2, is what's called the elliptic braid group. And it has generators, just as a group, of sort of three kinds. So the first kind, which we'll call T1 up to Tn, n being the number of points, just generate a copy of the usual braid group of the plane. Okay, so as is you can see drawn, the generator T sub I simply takes the ith and I plus first one of our n points and rotates one, say, clockwise around the other. The second, say, clockwise around the first. Okay, so we have a copy of the braid group of the plane sitting inside our elliptic braid group. And we also have two other families of generators. X1 up, sorry, I suppose I've already made a mistake in my indexation. Let me correct things. So I suppose I really want to be thinking about n plus 1 points on the torus, in which case we'll have n simple transpositions. And then we'll have n plus 1 generators, one for each point, x sub I and y sub I. So what do these x sub i's and y sub i's do? Well, the generator x sub I picks the ith one of these points on the torus and makes it take a little trip around, say, the horizontal cycle of the torus. And similarly, we have a generator y sub I, which makes the ith point take a trip around the vertical cycle. All right, so together, these generators generate this elliptic braid group. And the relations can be described in the following way. So as we said, the T sub i's generate a copy of the braid group of the plane, as is sort of topologically obvious. And also fairly clearly, the x sub i's commute among themselves, as do the y sub i's. And you can easily draw some pictures to convince yourself of the following cross relations among the generators. Namely, we have Ti, Xi, Ti is Xi plus 1. So Ti is sort of, in a sense, implementing the translation along the Dinkin diagram, and similarly for the y sub i's. And then we have various cross relations between the x's, all of which, in view of the relations here, can be sort of generated or follow from the following one, which says that x1, y2 is x2, y1, t1 squared. Okay, good. So this is the elliptic braid group, the group with these generators and these relations explicitly. And then we come to the definition of the Cherednik's double affine Hecke algebra. So it's an algebra which we'll think of as being an algebra over the ring of rational functions in two formal indeterminates, Q and T. And it's going to be a quotient of the group algebra over over rational functions rather in Q and T of the elliptic braid group by these sort of Hecke relations. So we have one for I running from 1 up to n, one less than the number of points. And these relations say the sort of quadratic relations on the T sub I is saying T sub I minus Q inverse T times T sub I minus Q inverse T inverse is equal to 0. Okay. So this is the Cherednik double affine Hecke algebra of type A sub n. And one nice thing that sort of comes straight out from this topological description we've given is that it comes with an action of the mapping class group of the torus, namely the modular group SL2Z, and explicitly in terms of these generators of the elliptic Frey group, that action looks in the following way. So again, let's remember that the modular group, you can think of it in various ways, but one convenient way to do so is in terms of the group generated by these two 2x2 matrices, S and let me call the other one tau to distinguish it from what we've been calling the T's. Explicitly, the action is given in a sort of very explicit way. So this S transformation, sort of operation swapping the sort of symplectic homology basis for the torus, sends the y1 to x1, sends x1 to x1 y inverse x1 inverse, and obviously preserves the T sub i's. Okay, so this is obviously these T sub i's are sort of insensitive to isotope because they're all taking place within some small little local neighborhood. And so that's the S generator of the modular group, and the T generator. So say this T corresponds to Dane twisting around the Y cycle, so it preserves the Y cycle and it sends the X cycle to X1 Y1 inverse, and again preserves the T sub i's. Okay. So what we are going to be interested mostly in this talk is a certain subalgebra of the DAHA called the spherical subalgebra. And one way to think of it is a subalgebra generated by certain elements, and those elements are going to be the following. So let's write E sub k for the kth elementary symmetric function in some number of commutative variables. All right, so remember that the x sub i's form a commutative family, as do the y sub i's, so it makes perfect sense to speak of the kth elementary symmetric function in the x's, as it does to speak of the kth elementary symmetric function in the y's. And if we take all of these elementary symmetric functions from the x's and y's, like k e sub k, where k ranges from 1 up to the number of points, then these will generate a subalgebra of the double affine Hecke algebra over rational functions in Q and T, and this thing is called the spherical subalgebra.
Sorry, may I ask, is
Yes.
this SO2 action the actual action or some action up to central extension?
Yeah, that's a good point. It's actually an action up to a central extension. Yeah, I sort of tried to sweep that under the rug, but it's an excellent point. Yeah, good. Thanks. Okay, good. So, one reason for the kind of for how useful and how nice these double affine Hecke algebras are is this great functional representation, polynomial representation introduced by Cherednik. So this representation, what is it? It's a representation of this spherical double affine Hecke algebra on the space of Laurent polynomial functions in n+1 variables. Let's call these variables little x1 up to little xn+1. And in fact, the action preserves the subring of symmetric Laurent polynomials in those variables. And it looks the following way. So remember, the generators of the spherical subalgebra are elementary symmetric functions in the x, generators of DAHA, and also those in the y's. So the generators ek of x act in the sort of simplest way possible. They just act by operators of multiplication by the kth elementary symmetric function and the little x's. Okay? And on the other hand, to describe how the action of the elementary symmetric functions in the Y generators of DAHA look, well, they're going to be acting by some kind of Q difference operators. All right, so to describe that, let's introduce the operator gamma sub I, acting on the space of Laurent polynomials. It just simply takes the function f of x little x1 up to little xn plus 1, and then scales the ith argument x sub I to q times x sub I. So sort of dilation by q in the ith coordinate direction. So then the generator corresponding to the kth elementary symmetric function of the y's acts in this polynomial representation by this famous Q difference operator, the kth Macdonald Q difference operator. So how does this fellow look? Well, notice that it's a rational Q difference operator, but it actually will preserve the subring of symmetric Laurent polynomials. And the way that it looks, the kth one of these Macdonald operators is gotten by summing over all k element subsets of, if you like, our n plus 1 points, 1 up to n plus 1. Then we have a product, one of the indices of which is missing my formula, so let me add it in. So we take the product over all elements I in the subset, I, and all elements j that are not in the subset, so kind of a rectangular product of size k by n plus 1 minus k. And then we have this definition parameter t times x sub I minus x sub j over x sub I minus x sub j. And then we have this, the shift part of the Q difference operator, product over all little I in a subset big I of gamma sub I. So we dilate by a factor of q all of the variables appearing in the subset I over which is appearing in the summation. Okay, so these are these famous Macdonald difference operators. They're rational Q difference operators, as we said, but preserve the subspace of symmetric Laurent polynomials. And what the nice thing is that they together have simple spectrum, and their eigenfunctions are given by the Macdonald polynomials. Okay, so so the sort of goal for what I want to explain in the rest of the talk is to construct an sort of an alternative functional realization of this spherical double affine Hecke algebra, on which the generators of DAHA, which in the original functional representation act by the Macdonald operators, are going to act by some Laurent polynomial difference operators. So difference operators no longer having denominators of the form we see in this expression for d sub k. Okay, right, and this construction is going to have kind of a combinatorial slash topological flavor.
Excuse me, Gus.
Yeah.
Why do you want that?
Why do we want them?
Yeah.
Yeah, good. So the main reason really, well, okay, well, there's a couple of reasons, but I think that the main one comes to the question of trying to understand in some simpler or more uniform terms this action of SL2Z, or central extension, on the double affine Hecke algebra. This polynomial representation is very nice, but it's not really so clear the kind of compatibility with the action of this SL2Z. In particular, like if you want to write, some kind of integral kernels for, say, this S transformation or whatever, I mean, I don't really know of any way to do that in the standard polynomial, well, in the standard functional representation. Whereas in this new one, it'll be transparently obvious how to do so. Right.
Thanks.
So yeah, that's really the motivation.
Mm-hmm.
Are there any other questions about this part before we move along? There's also probably a good point to mention something I shamefully forgot to earlier, which is that the rest of the talk is based on joint work in progress with Philippe di Francesco, Rinat Kedem, and Sasha Shapiro. Good. All right. So now, yeah, Andre has a question. So, so it's a question about the integral kernels for these operators. So what's certainly true is that the operator T is just given by a Gaussian integral representation. But the S one, yeah, I'm not so sure. But anyway, it'd be interesting to hear about afterwards, perhaps. Okay, good. All right, so the kind of the starting place for the construction of this different functional representation is a quantum integral system called the open quantum total chain. So I want to sort of give a brief kind of partisan recap of how I like to think about this integral system. I know that there's many other ways of doing so, but sort of this is the one that I'd like to kind of focus on for the talk. So I'd like to think about this open key difference total chain as the quantization of an integral system on a certain double Bruja cell inside of the group SLN plus 1. Okay, so let me unpack what I mean by that. So let's fix a pair of opposite Borels inside of SLN plus 1, we'll call them B plus and B minus, and we'll let H be the corresponding Cartan torus. So then the Weil group of SLN plus 1 is generated, of course, this is a symmetric group, and so it's generated by the simple reflections S1 up to Sn. Sort of, I suppose, strictly speaking, lifting each element of the Weil group to an element of the normalizer of the torus. The group SLN plus 1, we can break up into double cosets for the Borel B plus and the Borel B minus. And these double cosets, of course, are indexed by elements of the Weil group. So for every pair of elements of the Weil group, U and V, we can look at the sort of intersection of the corresponding Bruja cells, B plus, double coset, B plus, U, B plus, with the double coset B minus, V, B minus. Okay, and we'll call this fellow G, U, comma, V, and it's called the double Bruja cell corresponding to the pair U and V. So obviously there's a whole bunch of these we can consider, but those we'll be interested in the talk are those corresponding to the case where U and V are both the same Coxeter element of the Weil group. So it really doesn't matter which one you pick. Okay, so first of all, remember that a Coxeter element means that each simple reflection appears exactly once in the kind of reduced decomposition into simple reflections. And for concreteness, let's pick our Weil group element, Coxeter element, to be the product of simple reflections just in the order along the Dinkin diagram, S1, S2, all the way up to Sn. Okay, so in this case, the corresponding double Bruja cell has dimension 3 sub n. And when we take a quotient by the action of the Cartan torus by conjugation, we end up with a variety of dimension 2n. And so this is going to be convenient to kind of actually coordinatize or parameterize at least an open subset of this subvariety in the following way. So remember, what are elements in here in this double Bruja cell? Well, they're matrices in SLN plus 1, and we're going to kind of present those matrices by factorizing them into products of elementary matrices. So in particular, we're going to obtain an element in this Coxeter double Bruja cell GC, comma C. We're going to consider matrices that admit a factorization into elementary ones of a very particular type. Okay, so to describe what it is, let's first introduce these elementary matrices, E sub I, which is a matrix which is the identity matrix, except we also have a 1 in the intersection of the ith row and the I plus first column. So stuff like this. This would be E sub 1 for SL3, and the Fs, which is the transposes of the E's. Okay. And then we're also going to introduce this kind of, if you like, co-weight parameterization of the Cartan torus. And the way I'm writing things here, okay, so let me first just explain the formula. So we're going to consider elements of the torus H sub I of A, where we take the entry A repeated along the main diagonal I times, and then follow up with the rest of the entries in the diagonal being 1. Okay, so of course this element does not lie in SL1 plus 1. So really what I'm thinking, strictly speaking, I'm thinking about dividing by the appropriate n plus first root of the determinant to normalize things to be determinant 1. But really it's sort of some inessential thing which introduces a lot of ugliness into the formulas and not a lot of insight, so I'm just going to kind of pretend it doesn't exist for the rest of the talk. Anyhow, the kind of factorization which these elements of this Coxeter double Bruhat cell will admit looks the following way. Namely, they're matrices that we can factor in the form, the following form. So we are going to introduce 3n non-zero complex numbers that we'll call y1 up to y2n, and then an additional n that we'll call z1 up to zn. And then these matrices admit a factorization in the form h1 of the first complex number of y1 times this first elementary symmetric matrix e1. Okay, and then we have h1 of y2 times f1. And then we just repeat this kind of block of 4 elementary matrices, an additional, I suppose, n minus 1 times, each one incrementing the index on the h's and the e's and the f's by 1. Okay, so we have this big product all the way up to hn of y2n minus 1 times en times hn of y2n times fn. And then on the end, we stack just a product from I is equal to 1 up to n of h sub I of z sub I. Okay, so this is all probably looks a bit unenlightening, but sort of a much, I think, clearer way to think about it is using the following kind of graphical representation in terms of account of representing entries of this matrix as counts of paths in a directed network. So let me draw a picture of the network for SL3. It'll be sort of, I think, completely clear how it generalizes to higher rank. So we have this network with 3 horizontal lines that kind of flow from left to right. And then the way you should think about the correspondence between this network and the factorization above is that these complex numbers y1 up to y2n, z1 up to zn, they live on the faces of this network. Okay, and so these kind of these Cartan elements live on the faces, and the elementary matrices EI and FI, they correspond to vertical edges joining the horizontal pairs of the horizontal ones. Okay, so this first vertical edge we have pointing from the first row to the second row. This represents the elementary matrix E sub 1. This second vertical one, the matrix F sub 1, points up because it's the transpose of the E. We have E sub 2 and F sub 2. Okay, and then to recover the just because of how the way that matrix multiplication works, to recover the entries of our matrix, which is the element of the double Bruhat that we're parameterizing, we simply to get the ijth entry, we simply take the weighted sum over all paths in this directed network from the ith source on the left of the picture to the jth sync on the right of the picture. And what is the weight of one of these paths? Well, you simply take the product of all of the complex numbers attached to the faces below the path. All right, so for example, in this network we've drawn here, if we want to calculate the 2, element of the corresponding matrix, we need to sum over all paths from vertex 2 on the left to vertex 2 on the right. And we notice that there are, in fact, 2 of these. There's kind of the path that just runs straight along. And then there's the path which runs straight along, but takes a little detour down like that. Okay. And I suppose in this formula, I've neglected to include an overall factor of z sub 2, which will disappear in a second anyway. Okay, so yeah, these 2 paths, the kind of smaller one has weight y3 times z2. We take this face and this face, and the larger one we've also taken the face y4. All right, good. So so this gives a parameterization of an open locus inside of the double Broussard G C, C. But remember, what we're really interested in terms of constructing this total chain is the quotient of that double Broussard by the conjugation action of the torus. So what does taking the quotient by that action amount to in terms of the pictures? In terms of these networks? Well, it simply amounts to gluing the network on the cylinder by identifying the boundary faces in pairs. Okay, so really, this is the point at which these z sub i's are going to disappear and become identified with the y's on the other end. So this z sub 1 is now going to be glued to the y sub 1 on the other side, identified with the y sub 1 on the other side, and this z sub 2 is going to be identified with y sub 3. Okay, good. Right, so we I have claimed that this quotient of the Coxeter double Broussard by the torus is going to be the phase space of some integrable system. So we should be able to see some Poisson structure there. And let me describe in these graphical terms how one constructs that Poisson structure. So the first kind of observation to make is that vertices of this network come in sort of two types. There's vertices which have exactly one. Okay, let me maybe just sort of circle. So there's vertices that have exactly one incoming edge. For instance, these fellows I've circled in red here. And there are also those, and everything else has exactly one outgoing edge. These guys I've circled here. And so let's sort of agree that we'll call those with exactly one incoming edge black vertices, and those with exactly one outgoing edge, exactly one outgoing edge white vertices. Okay, so now this graph is going to become kind of a graph where the vertices have two colors. In this case, it's actually bipartite, at least before we glued it onto the torus. And in order to see the Poisson structure, one simply draws the dual graph to the original network in the appropriate sense. So what do I mean by that? I mean that whenever we see an edge in our network connecting a black vertex with a white vertex, we draw an arrow in the dual graph in such a way that, a directed arrow in the dual graph, in such a way that as we go along this directed arrow, the white vertex lies on our right. So for instance, we have an arrow from y1 pointing to y2 because there's this, this edge between the black vertex here and the white vertex here. And the directionality is chosen so that the white vertex lies on the right. Okay, so we dualize the graph in this way. And when we glue things up on the cylinder, as we mentioned, we obtain the following directed graph down here. In this case of SL3. All right, so so this directed graph governs.
Sorry, can you repeat the recipe for drawing the edges in a dual graph? I didn't understand.
Of course, yeah, right. So the recipe is that for each edge in the original network that connects a black and a white vertex, you dualize in the following way. So you draw an edge of the dual graph such that the white vertex stands on the right. As you travel along the directed edge of the dual graph.
Okay, thank you.
Good.
So Gus, this is just classical open AN to the system, right?
Correct. This is classical. Well, this is
relativistic.
Relativistic, yeah. Classical relativistic AN total system, open total system, exactly. A lot of adjectives, yeah. Okay, so this directed graph we've produced, this dual one, the one whose edges are shown in blue, governs the Poisson structure in the following very simple combinatorial way. So remember that vertices of this dual graph correspond to faces of the original network, which is to say these these factorization parameters y1 up to y2n, which is to say coordinate functions on this open locus of the double Brouillard cell. And the Poisson bracket between any pair of these coordinate functions is always proportional to their product. And the coefficient of proportionality is just the number of directed arrows from y sub I to y sub j, if we're calculating the bracket between the ith and jth one of these coordinates. So for instance, if we wish to calculate the Poisson bracket of y1 with y2, we'll end up with 2 times y1, y2, because we have a double arrow in this quiver over here. Whereas, for instance, y1 and y3 will just Poisson commute, and y2 with y3 will be y2 times y3.
Sorry, I'm confused about one thing. So in your original graph, some of the faces were labeled by z's, not by y.
Exactly, yeah, right.
What
so
happened
the reason
to that?
is, yeah, so the place where the z's disappears when we took the quotient by conjugation by the torus to glue the graph onto a cylinder. So when we do that, this Z1 is now glued to the Y1 on the other side. Yeah.
So this is now happening on the cylinder. So
exactly, this is now happening on the cylinder.
And so no z's at all.
No z's at all. Right. I mean, really, we've passed to a well. They're really, strictly speaking, still there. We've really passed to the subalgebra. In this case, generated by y2, y4, y1, z1, y3, z2. Yeah, because the diagonal action of this torus has the effect of, the first generator will scale this y1 by t, and will scale the original z1 by t inverse. So to get the invariant combination, you take that product.
Gus, a stupid question. When you put something on the cylinder, you should expect that it's going to be periodic, affine to the. Why it's still open?
Yeah.
It will be periodic if you put it on a cylinder in a different direction. If it will be on a torus, then it will be affine.
Yeah.
Gus, may I ask some technical question? Because
in
your picture, you have this quartic vertex in the middle.
Yes.
It's something that we usually don't have. So something that, say, in four pointer, we would expect that actually y1 and y3 do not commute.
So this quartic vertex is easily resolved, and the way to resolve it is sort of easily seen from the sort of Lie theory, which is that these generators F1 and E2, which correspond to the edges emanating, the vertical edges emanating from it, commute with one another. So you can actually just resolve this guy. I wonder where the best place to do this is. Let me try and do the following. Copy. So you can resolve the picture in the following way into a pair of 3 valence vertices at the cost of making the graph no longer bipartite, which, I mean, okay, you can bipartite.
But then this, so you mean that to make this variable still commuting, right? That's what you want.
Right, yeah. So you can always resolve things to 3 valent vertices at the cost of introducing, you know.
Okay, I say it was a technical question, so that's
good. Cool.
Gus, and I do not understand what you told Lenya. Who is non-commuting here? By now, everything is commuting. Yeah, it's just classical theory.
Right. I think Lenya was referring to Poisson commutativity.
Poisson commutativity. Yeah, that's what I mean.
Yeah. Good.
But
right.
So you mean that you just add an extra variable in this way, which will be absorbed by multiplication into some other?
Right, exactly. Yeah. Good. Okay. Right. So so now we have a handle on the at least a coordinatization of an open locus inside the phase space of this integral system, including its Poisson structure. And so now we're ready to describe the Hamiltonians, which also have a really nice, simple description in terms of this kind of combinatorics. So the kth total Hamiltonian, remember, just theoretically, is the trace of the group element in the kth fundamental representation of SLN plus 1. And what does that correspond to graphically? Well, by this usual kind of Lindstrom, Gessel, Viennot, non-intersecting lattice path yoga, in order to get the trace in the kth fundamental representation of a matrix like this. Okay, well, before even getting to that, right? The first total Hamiltonian is just the trace of the matrix, right? So to get that, what we're supposed to do is we're supposed to sum over all paths that begin at one of the 3 vertices on the left and end at the same vertex on the right. So we sum over all vertices I of, and then over all paths connecting I to I, weighted in the usual way. All right, so how to get the high Hamiltonians? Well, again, by this sort of non-intersecting path, Lindstrom, Gessel, Viennot yoga, this trace in the kth fundamental is going to be given by taking a sum over all subsets of 1 up to n plus 1, all subsets of vertices at which we begin of size k. Now we sum over all k tuples of non-intersecting paths in the directed network that connect those I vertices with themselves on the other side after taking a trip around the cycle of the cylinder. And as the weight of one of these sort of path, k tuples of paths, we just take the product of the weights of all of the paths that are in the ensemble. Okay, and this, by the usual kind of proof by involution reasoning, will compute the trace of the original matrix in this case, fundamental representation. All right, so now we know everything about the integral system in the usual sense of integrability. But this integral system is, many people in the audience have sort of were responsible for discovering, has some nice kind of additional structure, which is it's what's called a cluster integral system. So don't worry, I'm not going to kind of inflict upon you any long generalities about cluster algebras, but I just want to kind of point out that this quiver, this directed graph that we obtained by dualizing the original network, we saw that it governed the Poisson structure on the phase space, but it turns out to also play kind of a dual role related to giving a global, not just local description of the phase space. So we saw here that we described one particular kind of open locus of phase space, which was just isomorphic to a sort of split torus, GM to the power twice the rank. But really, this quiver secretly tells you how to obtain a global description, at least up to some locus of codimension 2. So a global description as far as observables can see. And the way that it determines that global description is by determining a combinatorially defined system of additional sort of charts on the double Brouillard cell, along with combinatorially defined transition maps, rational transition maps between them. Okay, and some of these charts, not all of them, but a sort of tractable family of them, correspond to certain sort of elementary local transformations of the network. So let me sort of just illustrate one such local transformation, which is probably some pretty familiar thing to us you guys. But so imagine we sort of see a piece of network that looks the following way. So we have a collection, a sort of a square face of our network, if you like, with alternating black and white vertices, such that those black and white vertices are all 3-valent, as Leonia pointed out earlier on. So in that case, one can perform the following sort of local move on the network that simply replaces simply sort of inverts the coloration, sort of takes the negative of the photo, if you like. So the black vertices have now become white vertices, or white have now become black. All right, and now you can convince yourself that if you reparameterize the faces of the faces of the new network are now going to have some weights y1 prime, y2 prime, y3 prime. And if y1 prime, y2 prime, and y3 prime are related to the original y1, y2, y3 by these formulas down here, then you can easily multiply some matrices together to check that at least after normalizing things to be determinant 1, or equivalently after taking ratios of entries of the matrix, you'll get the same count of paths from the sources to the sinks. Okay, and this is sort of the prototype example of a cluster transformation. Good. All right, so
can you repeat, what do you mean by sum of?
Yeah, good. So what I mean is that how do we get we'll get a 2x2 matrix from each of these networks, and to really concretize it, one should, I suppose, number the horizontal lines in this graph. And for instance, the 1, 2 entry of this top matrix is just going to be, so we sum of the paths from 1 to 2, so we're just going to pick up a single such, which gives us weight y sub 1. Whereas in the second network, we're also going to have a single such path, but it's going to have weight y1 prime, y2 prime. And yeah, and as I mentioned, in order for these formulas down the bottom to work correctly, you either need to normalize things to have determinant 1, or look at ratios of entries of the matrix.
Maybe not about my question. I asked, what do you mean by sum of in brackets? So something do not correspond to the elementary transformation.
Yes, up here, right. So really, there's this sort of local operation at the level of quivers or directed graphs one can perform on this initial directed graph we got from our initial network. Now, some of those local transformations that basically involve mutation at 4-valent vertices with alternating incoming and outgoing edges when you draw the quiver on a cylinder, those will correspond to elementary moves of the network exactly like the one I described. But this quiver is sort of wild mutation type. And there, if you start clicking on random dots, you'll quickly end up with, vertices with 12,000 arrows pointing in and 7,000 pointing out. And when you mutated those, you're doing some funny kind of birational transformation, which doesn't correspond to a combinatorial transformation of networks in any kind of obvious, in any way at all, really.
And what to do with them? With this?
I don't really know. So the first comment is that they're not necessary to describe the, to cover the variety by charts up to co-dimension 2. For that, you only need those coming from networks. So in a sense, observables can't see the fact that we can't handle these other charts combinatorially. So they're perhaps not so important, but yeah.
Okay.
Okay. Mm-hmm. All right. So so now let's say a word or two about quantization. So which we'll need to do in order to speak of algebras rather than non-commutative algebras like our double affine Hecke algebra. So the basic idea is very, very simple here. We're just going to promote these coordinates y1 up to y2 sub n that lived on the faces of the network. Remember, we're parameterizing the group element by factorization. We're going to promote these coordinates to Q difference operators on the ring of functions in the ring of Laurent polynomials in n+1 variables. Okay, so let's call these variable, I don't know, maybe z is a poor choice considering I already used it for something else, but let's stick to it to now. So y1 up to y.
These are different from these you were using before.
They are. Let me call them capital Z's. I don't know if that will help or hinder the.
Is it just transformation from SLN to GLN?
The Z's?
Yes. I mean these ratios. You just instead of roots, you take the weights.
Yeah. That's the idea. Yeah. Huh? Yeah. Right. So okay. So how does this quantization work? Well, we are going to promote each of these toric coordinates y1 up to y2n to a certain Q difference operator on this ring of Laurent polynomials in the Z variables, of which there are n+1, one more than the rank of the group. And the way it works is very simple. So the odd, so if you like one sort of way to think of this, funny way to think of this directed graph that we have over here, that we get from the double Broussard and SLN+1, is that it's like sort of two copies of, you can kind of think of the variables living on the left as one copy of a Dinkin diagram of SLN+1, and those on the right as another. Okay, so these odd variables that correspond to kind of sources of the double arrows in the directed graph, these just act by multiplication operators on this Laurent ring. So the 2i minus first, one of these odd variables, just acts by the operator of multiplication kind of by the first simple root, but by the ith simple root in the z's. So y sub 2i minus 1 acts by multiplication by z I plus 1 over zi. And correspondingly, the even y variables act by the sort of corresponding canonically conjugate momentum operators. So y sub 2i acts by what we'll call p alpha sub I, which is pi plus 1 over pi, where what is pi? Well, again, pi is just this operator which takes a Laurent polynomial in the z's and dilates the ith coordinate z sub I by a factor of q. Okay, so in this way, our commutative total Hamiltonians are promoted to a set of commuting polynomial Q difference operators, h1 up to hn+1, on the ring of Laurent polynomials in Z1 up to Zn. Okay, and the sort of point I'd like to kind of emphasize here is that these total Hamiltonians are really polynomial Q difference operators. So there's no, they're not rationals. There's no denominators involved. because remember these Toda Hamiltonians were just given by summing over paths in the network. Each path had a weight which was proportional to the product of a bunch of, which was equal to the product of a bunch of these y's. And each y is just a polynomial Q difference operator, so therefore so are the Toda Hamiltonians. All right, so the sort of motivation for how we can kind of bootstrap these Toda Hamiltonians into a realization of DAHA kind of, well, at least our motivation came from some result with Shapiro from a few years ago, where we constructed a sort of complete orthogonal set of eigenfunctions, psi of z, depending on kind of spectral coordinates x1 up to xn plus 1, for these Q open Toda operators, with the property that the action of the kth Toda operator on this eigenfunction psi z with spectral label x is given by multiplication by the kth elementary symmetric function of the variables x. Okay, so in other words, under the sort of spectral transform for the Toda chain, these Toda Hamiltonians become operators of multiplication by the kth elementary symmetric function in a commutative set of variables x1 up to xn. So of course, the idea is that if we want to cook up a sort of polynomial functional realization of DAHA, then why don't we take these Toda Hamiltonians in this realization we've just described to be half of the generators of DAHA, okay? Because remember, the generators of DAHA were given by the elementary symmetric functions in these variables x, along with elementary symmetric functions in the sort of variables attached to the dual cycle of the torus and elementary symmetric functions of the y's. So the problem that we face is we now have half of the generators, sort of easy half of the generators of spherical DAHA, how to kind of see the interesting half, how to see the Macdonald operators. And that's what I want to address in the remainder of the talk. And the way we'll do it is sort of a very identical, essentially, flavor to the way we construct the Toda operators. So it's again going to be using the combinatorics of directed networks and corresponding cluster algebras. So the first step of the construction is that we're going to take our quiver, our directed graph, to describe the Poisson structure and cluster structure of the open Toda phase space. So that is this one consisting of vertices y1, y2, y2n minus 1, y2n, and we're going to augment it by a single additional vertex that we'll call y sub 0. Okay, and this additional vertex y sub 0 is connected up by the red arrows that you can see in the picture to the original Toda quiver. What difference operator does this new variable y sub 0 correspond to? Well, now this involves the auxiliary parameter t for the DAHA, namely this y sub 0 acts by t times zn plus 1 over z1 times pn plus 1 over p1. Okay, good. So now, as you can kind of see from the picture, this quiver naturally lives not on the cylinder, but now on the torus, because we sort of have now two directions of periodicity. The original horizontal one that was the cylinder on which the Toda quiver lived. In addition to that, we have the new vertical one that we've gotten by joining this new vertex y sub 0. So the next step of the construction is to consider the dual graph on the universal cover of the torus. So let me draw a picture, or show a picture that I already drew for GL3. So we're just going to kind of unroll this this quiver, the dual graph of this quiver, in both directions. Horizontal, which corresponds to our the way we were thinking about Toda originally, and now also vertical, which corresponds to the addition of this new vertex y0.
Gus, may I interrupt you for a second?
Of course.
Andrei told some time ago that making the system live on the torus, it makes it periodic, but you still have an open.
Right. Yes. So this is a different way of putting the system on a torus. Yeah. So really the quiver for the one which
sorry,
looks,
Gus. Gus, but it looks like you can take a quiver corresponding to GL3 hat and then just glue 2 extra vertices into this your single Y naught. I don't know if it has any sense, but it looks very similar.
Yeah, so you mean obtain this quiver from one corresponding to
on
a cell in
on your picture. Otherwise, this rectangle corresponding to Y naught would be just divided into 2 squares.
Into 2 squares, right? Yeah.
Yes. And if you do this, then this is, I mean, answering to Igor's question. At least at these levels, it looks very similar to some manipulation with GL3 hat.
Yeah. Right, but yes, so that's a good point. But also in answer to Igor's question, the most standard way of realizing the periodic relativistic total chain is to put the quiver on the torus in a somewhat put the system on the torus in a somewhat different way that corresponds to a quiver kind of the form up here. Yeah, whereas here we really have something more like.
No, sorry. So that what you drawn is SL2 hat, and if you just add one more line, then you get the same way. Well, I mean, at least it's the same direction.
Yeah.
But again, I don't yet see what is your Y naught, and can you think of it in the way which reminds this affinization?
Yeah, it's a good point. A good question. All right, but for the moment, let's sort of continue to think in these terms of having a single vertex, a single face rather, y sub naught, so that the dual graph really does look as indicated in the picture. And now I want to describe for you how to see the networks inside of this large double periodic network to describe both the Toda and the Macdonald operators. Okay, so the first observation is that we can obviously spot inside of here, as we kind of scan along in the horizontal direction, a copy of our familiar network we use to compute the Toda Hamiltonians. Namely, if we kind of come down here and isolate this little piece of network that I put these purple braces around, we see exactly a copy of our familiar Toda network. So if we count paths from the 3 red sources to the 3 red sinks, we'll get an n+1 by n+1 matrix, well, in general for GL n+1. That will, and traces of that matrix in various representations will recover as the Toda Hamiltonians. On the other hand, how do we see the Macdonald operators? Well, for that, we know that it should somehow be related to the dual cycle on the torus, and indeed it is. So if we now look at the following little piece of this black-white graph, where that I've indicated in between the green braces, and we now count all paths from the blue sources to the blue sinks, we'll get another n+1 by n+1 matrix. Let's call that one Mij. And now, what we show with Philippe, Rinat, and Sasha is that, again, taking H sub k to be the traces of the red transport matrix in the fundamental VK, and taking D sub k to be the traces of the blue transport matrix in the kth fundamental, gives a representation of the spherical part of the double affine Hecke algebra by polynomial Q-difference operators on this ring of Laurent polynomials in Z1 up to Zn+1. And the one of the nice things about this sort of alternative function realization is that the action of the mapping class group is really very, of SO2Z is really very transparent and very uniform. Namely, it acts always by cluster transformations. So in particular, this issue of writing integral kernels for the various mapping class group elements is now sort of can be treated in a completely uniform way. And all of these integral kernels factor into elementary pieces just coming from quantum logarithms. So it sort of gives very simple.
Sorry, Gus, just forgot. You had this originally introduced Y variables when then you present as a ratio of some z's, yeah? And you have either these z's or a shifts operator in these z's.
Right, correct. Yeah.
So how then, what is Y naught? So
right.
Where it appears?
Yeah. Good.
Is it just a parameter?
No. So Y naught is also, it corresponds to the, exactly what you think it would be.
This is the expression?
Yeah.
And sorry, what is this purple T?
So that's the T from DAHA.
This is T from DAHA. So it's a ratio of z's time ratio of pi's, yeah?
Yeah, exactly, yeah. And it corresponds to sort of the root you would get when you glue the diagram to a segment.
Well, I don't know, of course, but it looks really similar to gluing of these 2 points of the affine curve.
Of GL3 hat, yeah.
Okay, thank you.
Yeah.
May I just mention that the Poisson dimension is not affected by adding this Y naught, right?
Precisely, yeah, exactly.
Because before there was no central.
It had full rank, yeah.
One.
Correct. Good. Right. Yeah, so the...
Can I also ask about this theorem? So you write here H and D are certain traces. Actually, I don't understand. Can I think that H and D are elements of this algebra with generators Y's and which is quantization of the Poisson algebra with quadratic bracket?
Absolutely, yeah. So these guys are elements in this algebra with the these relations that yi yj is equal to q to the number of arrows from I to j yj yi. That's right.
And this algebra is this quantization of the algebra of the Poisson dimension 2n.
Correct.
And the DAHA is of n+1 braids, yes? I saw that this DAHA should have dimension.
Yeah, you're right. Yeah, you're right. So I've swept something under the rug, which is the issue of frozen variables. Yeah, you're absolutely right. There's really, in addition to this quiver, there's an additional pair of frozen variables that really should be drawn. So yeah, there's two frozen variables which contribute the extra, the extra 2 Poisson dimension. Yeah, that's also something I'd hope to sweep under the rug, but that's a good point. Thanks.
So they should appear also on this picture with blue and red. Oh, in any picture.
Yeah, good. So where they appear there is really related to the issue of what it even means to count paths in a network like this at all, right? Because remember, we said something like the weight of all paths below your path. But when you have an infinite network, what on earth does below mean? So really, the thing is that you need to have 2 kind of direct C's of faces, as we were saying. One for doing the red network and one for doing the blue network. And this is the origin of these frozen variables, basically. Yeah, again, some funny technical issue that tried to sweep under the rug. But you're absolutely right. It's crucial to have these present variables to get the correct relations.
Sorry, Gus, and one more question. So
yeah.
It's a little bit misleading for me, this GL3. Funny. So these three red dots, one above another, just corresponds to the case that you have GL3, right?
Correct. Yes.
If you have GL4, then you would have one extra line,
exactly,
and you will have 4 red dots. In
Precisely.
This, you also have to choose 4 copies in vertical direction, right? And consider these 4 blue dots. But still, I'm somehow confused because the multiplication of matrices in horizontal direction is just a construction in this cluster coordinate of some group element, say, a-la Fokan-Gonsherov. Yeah,
exactly. Yeah,
and this is this matrix G.
Yes.
And then all its invariants are mutually Poisson commuting.
Correct.
But what I don't understand is who is your matrix M?
Right.
In these terms, which turns to be Macdonald operator.
Right. So the matrix M again is just counting the paths from the n+1 blue vertices on the bottom to the n+1 blue vertices on the top. So it corresponds in some strange way to again a factorization of an n+1 by n+1 matrix into elementary matrices. But now the factorization parameters are not independent. So if you like, it's like a fold.
Sorry, just maybe it's a bit too fast for me. Just you said about factorization. Can you present it as multiplication of some?
Oh, absolutely, absolutely, yeah.
And you will give a formula, yeah?
Yeah, sure. Absolutely. So that's really the key to discovering these cluster action of the mapping cluster, is to boil everything down to factorization in SO1+1. Yeah. So I'll try. I think I'll illustrate with an example. Hopefully, it will be somewhat enlightening. But yeah. But basically, whenever you have a 4-valent, whenever you have a planar network such as this one, such as these pieces that are shown in green and in purple, you can essentially always interpret such a thing in terms of factorization in SLN. Okay, good.
Sorry.
So,
and when you say about passes on this lattice, yeah, you assume that the product of some variables is 1 or not, or you don't impose this constraint?
No, yeah, no question. No question by Casimir type constraints.
So when you can, okay, so there will be weights of passes will be below, yes?
Yeah, or to the right. I mean, it comes back to this issue of frozen variables. So sort of at the beginning of the construction, one needs to make a choice of kind of Dirac C for the blue network and for the red network. A sort of choice of the weight of the infinitely many faces to the left or to below.
Sorry, just reformulating Cole's question. The product of all y's is in the center of Poisson algebra.
Correct. Yes.
Is it T, Macdonald?
Yeah. It's this DAHA T.
Yeah, it's T. In your formulas, you just introduce T by hand.
Exactly. Yeah. I mean, T, if you like, is the Casimir for this, the product of all ways.
And another question, horizontal and vertical Macdonald operators or DAHA operators should satisfy some relations. Also from general R matrix written in papers of Geffner, Shapiro, Weinstein, we also should expect some relations among matrix elements of red matrix and blue matrix.
Correct, yeah.
So DAHA relations follow from those R matrix, yes?
Yeah, that's an interesting question. So the way that we prove actually that this gives a representation of DAHA doesn't actually go by direct verification of the relations. It rather goes by this construction of DAHA as a Coulomb branch of a quiver gauge theory for the Jordan quiver. But yeah, I imagine this is a really good point. I imagine it is probably possible to derive from scratch relations among the Toda operators and the DAHA operators just based on this kind of Shapiro-Weinstein network calculus. But that's not something that we tried. Okay, good. So I perhaps want to just finish off by perhaps doing an example again in this case of GL3 to kind of illustrate the way in which one can see the action of the SL2Z in terms of cluster transformations, or if you like, in terms of these elementary local transformations of networks that we described a little earlier when we were talking about the Toda chain. So let's think about it again in this case of GL3. What might this S transformation from the modular group look like? So remember, the S transformation is supposed to send the Macdonald operators to the Toda operators. It sends the Ys, generators of DAHA, to the X ones. And we want to derive this action of the S transformation on our polynomial representation by actually seeing this at the level of the networks. So we want to do some chain of local moves, in this case, it could just be one, on the network in order to transform this blue network we use to compute the Macdonald operators into this simpler red network we use to compute the Toda. So I'd like to just sort of illustrate how this works for SL3. So let me first kind of zoom in on the Macdonald part of the network that we use to compute our 3x3, in this case, matrix Mij. Okay, so we have our blue vertices at the bottom, the sources, the blue at the top, the sinks. We see that all of the paths from the blue sources to the blue sinks are sort of bounded by these two green paths I've shown on the left and on the right. Okay. So in particular, to make this look more like something that lives in the world of factorization in Lie groups, let's do something purely cosmetic. Let's turn our heads 90 degrees and sort of pull the green line straight. When we do that, we get a picture of the following form. And now again, this really does, ignoring these sort of boundary faces that are on top, this really does look exactly like the factorization of an element of GL3. Okay, so now, how are we going to see the kind of elementary transformations of the network that will take this network we have here and transform it into the network for the Toda, that computes the Toda chain Hamiltonians? So the first step that we're going to do is that we're going to kind of, remember this network is periodic in both directions, but certainly in what is now the horizontal direction. So we're just going to shift our fundamental domain a little bit in the horizontal direction to make our network look in the following way. Okay. Now what we can do is we can again apply this smooth that Leonia mentioned, which is to, when we have a pair of white vertices that are connected, we can merge them into a single white vertex. And by doing a chain of such operations, we can get ourselves to the second picture we have at the bottom of this page. All right. So now the neat thing is that we notice that these faces with y sub 0 labeling them are perfectly ripe for applying one of these local network transformations, right? Where we sort of take the negative of the photo, and now the white vertices become black vertices, and the black vertices become white vertices. So what we're going to do, right? And in terms of quivers, this corresponds to this operation, funny operation of mutation. So let me draw again the quiver. So we're going to mutate at this funny vertex y sub 0, which corresponds to doing on this graph this local move, taking the negative of the photo at all of the faces labeled by y0. So we apply this local transformation. Let me see if I can fit both on the one page at the cost of making things a little smaller. And we end up with a network at the that we see down here. Okay, but now notice something really nice has happened, which is that all the paths are constrained to lie within the these two that I'll draw maybe in purple. And if now we pull our purple lines taut, pull them straight, then we see exactly the network we had that computed the SL3 total Hamiltonians from the beginning of the talk. So in other words, doing a single mutation takes the traces of the M matrix that were formerly the Macdonald operators to the traces of the Q matrix, which were the total Hamiltonians. Okay, good. So yeah, I think that's some kind of a natural stopping place. Yeah, thanks very much for your attention.
Sorry, Gus, but can you write down just a formula for M as a product of some matrices?
Of course, yeah. So in this case, it will, and the way that it's done. So if one simply wishes to do that, one can ignore these kind of boundary pieces of the graph. And now, so now let's go through and orient everything up to see what these matrices ought to be. So remember, the white vertices are supposed to have exactly one outgoing, the black exactly one incoming. So we get something that looks the following way. And now we can just kind of scan our picture and read off what we have. So we also don't need these fellows. So here we have an E1. Here we have an F2. Here we have E1, F2. Here we have F1, E2. I forgot to do these guys. No, sorry, in fact, we don't even need this. Yeah. Yeah, so in this case, it corresponds to this product, E1, F2, E1, F2, F1, E2. So it's a non-reduced word.
And just H's correspond to the level, yeah? So it's
exactly,
like H1 of Y4, E1, H1 of Y,
exactly,
Y0.
Yeah.
Right. So you sort of add one extra Y0 to each of the levels, yeah?
That's right. Yeah. So in general, the way that one, one will derive such a the mutation sequence for the S transformation is to you'll obtain some non-reduced word in the Weil group Sn, and then you'll basically apply cluster mutations that reduce that word down to Coxeter, Coxeter.
But it will become on some more complicated combination of these variables.
Yeah, that's right.
Including this your extra Y naught.
Exactly, but there's new complicated combinations of just cluster mutations of the former ones.
Well, not only cluster mutation. I mean that they would depend on only on the multiplied. How to say? Multiplied compounds of these variables, yeah? So the number of independent variables in this
yeah, right. Yeah.
Is to n, but here it is constructed from something more.
Right. So
it a bit reminds me your construction of these todas on symplectic leaves of high dimension.
Right. Yes. So the interesting thing here is that the dimension is still 2n, or 2n plus 1 if you 2n plus 2 if you include the frozen variables. But the thing is that the face variables are now no longer independent. So it's sort of not particularly visible in this example of SL3 because it's kind of too small. But in general, you have a network that has roughly n squared faces. And of those, but only 2n face coordinates. So the faces will kind of be, will have labels that are very much not independent. It will just be, you have the single label appearing multiple times at vertices that live in the same fiber of the universal cover.
Sorry, but if you take this big cell in SL3, which is of dimension 6.
Yeah.
So it's the same dimension like you have here, right?
Yeah. So this is cyclically equivalent to the big cell. So like yeah. So if you shift the fundamental domain, you'll come to the big cell. Yeah. And the same is true in general.
Is it true generally or only in this particular example?
It's true generally. Yeah, it's true. So for GLN, basically what you'll start with is a word for the big cell, which is cyclically extremely non-reduced. By cyclically shifting the domain, you obtain a non-reduced word, and you reduce things down until you get to Coxeter, Coxeter. In which case, you come to the total network.
And can you somehow formulate this invariantly? So what gives you finally these Macdonald operators in terms of original Lie group? Or it's a stupid question?
I think it's a good question. So I think the sort of correct topological or invariant way to formulate this should go via modular spaces of local systems. So I guess I talked mostly in the examples about SL3, but a simpler case of this is really SL2, where the quiver we have is one I think we drew earlier. And now the quiver sort of degenerates to this case here. And this is exactly the quiver that describes the cluster structure for the modular space of framed PGL2 local systems on the torus. And so the natural thing one might ask is, well, why didn't you just, increase the rank of the group? Look at, PGL-N, local systems on the torus. And the problem is that the dimension of that variety is much too large, sort of roughly 2n squared, right? Because you have two commuting matrices. And really, I think what's going on invariantly is this the fact that you're really okay on a punctured torus, I should have said. on a punctured torus. So really, I think what's happening is that you have this punctured torus, maybe a puncture, and there's this constraint being imposed that this monodromy around this puncture ought to lie in this sort of mirabolic conjugacy class, which is like T times the identity plus something of rank 1. So I think really what's going on, and then really I think that in the most literal, and I should have said in this case here, then our tota, then really quite literally, the tota is the trace of the holonomial along the A cycle, and the Macdo is the trace of the holonomial along the B cycle. So I think really this picture will continue to be true if one carefully understands in cluster algebraic or combinatorial terms what it means to impose this kind of mirabolic conjugacy class condition at the puncture of the torus. But yeah, it's a good question, but it's something we didn't yet think too hard about.
I probably have some confusing impression that this torus with a single marked point should somehow correspond to trigonometric Ruyssinars.
Yes, it will. If so, it depends on the so you can set t is equal to 0, which corresponds to degeneration of the Macdonald of DAHA to this nil DAHA, or degeneration of the Macdonald operators to trigonometric Ruyssinars operators. So yeah, this corresponds to the case of a flat. To connections which are have where the holonomial is a rank 1 matrix around the puncture.
Sorry, and when you said that H and D are DAHA algebra, so I can just am I understand right that both of them are Laurent polynomials in cluster variables?
Correct, absolutely.
And cluster variables are monomials, Laurent monomials into P and X.
Yeah,
yes?
That's right. Yeah.
But when you wrote us initial formulas for DAHA generators, you got in Macdonald operators, you got rational functions.
Exactly. Yeah. So this is a different functional realization from the original one. And basically the way to go between them is to apply, the two representations, you just apply the spectral transform for the tota chain that I mentioned a little bit earlier. So, yes, so the idea is that we want to, if we want to transform these elementary symmetric functions in one variable set into tota operators, then we can apply the kind of inverse spectral transform. And when we do that to the D subcase, we'll get something, and that something turns out to be exactly computed by these counts of paths in the network.
Are there more questions? Oh, we have enough.
So I wanted to ask about this computations of path partition functions for tota and Macdonald cases. So do I understand correctly that though you draw this picture on torus, actually when you compute each of these partition functions, you cut some edges, and actually each time you compute this partition function on a cylinder, but there are two different cylinders.
Exactly, that's right. So it's the same way you'd compute holonomial of a local system. Yeah, you sort of cut into a little tube.
But can we say it equivalently that we are computing not these two path partition functions, but instead we consider this a big torus, maybe such that in the vertical dimension we have only one fundamental domain, but in the horizontal direction we have n+1 fundamental domains, and then compute partition function on this torus, a kind of dimer partition function, and then say that we are taking only some coefficients in this partition function corresponding to the horizontal axis and to the vertical axis. I mean to the contributions which have a zero A-cycle projection and zero B-cycle projection.
Right, yeah, I think that should be an equivalent way to formulate it, yeah. Certainly always possible to translate any sum of the networks into a corresponding counter dimer configurations, and so that should be right.
Yeah. So, but as I have a question, what happens in a sense that naively, if we compute such a dimer partition function, then all operators that we get should commute between each other. But in your case, as I understand, this vertical operators and horizontal operators do not commute.
Correct, absolutely not. But I think you will have to have two separate bipartite graphs for which you compute dimer configurations, one for the A cycles and one for the B cycles. I'm not sure it's possible to really do them simultaneously for exactly the reason you say, which is that sort of necessarily all of those coefficients in characteristic polynomial must commute with one another. But certainly it's possible to formulate separately each of the A and B cycles in terms of dimers. But I'm not sure. Yeah, I certainly that they.
But what is the reason for which we have to formulate it differently for A cycle and B cycle?
Yeah, simply because it's not possible to draw a network, a consistent network, which simultaneously will have the where am I? Yeah, which will simultaneously have the blue arrows up here and the red arrows down here pointing the way they do. It's not possible to consistently orient things in such a way. So really, the way I kind of think of it is you have this sort of underlying two-color graph, and then which knows all the information about everything, and then you want to compute some kind of observables. To do that, you have to sort of take some kind of matrix elements of the tensor this graph represents, which means you have to kind of specify some what's incoming and what's outgoing, which are the sort of V and which is V star. And then when you do that, you get something out, but there's many different ways to do so, and some give you the A cycle observable, some give you the B cycle ones. Yeah. That's not a very coherent thing, I know, but.
I see. So is it? So is the main problem basically that this path partition functions are not exactly dimer partition functions, or not?
I think the problem is it's not possible to put it to a bipartite graph on the torus without introducing, additional faces that you don't want to have, basically. And I think it's actually related to the fact that this thing lives really in a punctured torus, not a torus itself. So somehow if you try and put it on a torus in a naive way with the dimer picture, you'll end up with faces that kind of contain this puncture. And so you have to throw those away somehow, and it corresponds to cutting the thing into a cylinder in one of the two ways, I think.
Thank you. Well, I also wanted to ask, so in this spherical DAHA, we have symmetric polynomials of x, symmetric polynomials of y, but also symmetric polynomials in both sets of variables, like sum of xi, yi. Do you have any analogous construction which reproduces kind of other symmetric variables?
Yeah, that's a good question. Off the top of my head, no, it's not something we've thought about, but I imagine it's, yeah, I imagine such a thing should certainly be, certainly be doable. Yeah, it's a good question.
Thank you. Maybe the last question. Maybe I missed this. What is the product of this 5 variables, y0 and so on, y4? Is it fun or not?
So that's the DAHA deformation parameter T. So the Casimir for this Poisson structure. Yeah.
I see. So, thank you.
More questions? If not, then just thanks, Gus.
Thanks, guys.
Very nice talk. Okay.
Thank you.
Thank you.
Thank you.